everyone. Today we're going to have a look at soaps and emulsions. This is the next subtopic of Unit 2. It's Unit 2, subtopic 4. So, soaps and emulsions. Our learning intention is to investigate the products of alkaline hydrolysis of fats and oils and their uses. So this process is going to produce some soap, and we're going to have a look at soap structure, how soap cleans, and also a little bit about emulsions as well. So what is an emulsion, and I want you to be able to give an example of emulsion at the end. We have looked at alkaline hydrolysis before when we were talking about esters. This is a very, very similar mechanism, so hopefully it will be quite straightforward to follow. So, a starter question to start you off with. We have methyl benzoate is commonly added to perfumes and has a pleasant smell. A student carries out a reaction to produce methyl benzoate using the following apparatus. So you can see the apparatus set up here. The question is, the reaction mixture needs to be heated. Describe a safe method for heating a flammable mixture. So have a wee think about what that could be. B is suggest a reason why there is a small test tube filled with cold water in the neck of the tube containing the reaction mixture. So what you need to think to yourself here is what kind of substance is being produced, what kind of substances are in the test tube, and that should hopefully help you answer A and B. Just to help you, you did not use a small test tube. When you did this experiment, you used a wet paper towel, but this is a kind of problem-solving question and that you're having to apply your knowledge to a different context. So, soaps. Soaps, like I said, are produced by the alkaline hydrolysis of edible fats and oils. The process is known as alkaline hydrolysis because it's treated with an alkali. So the one commonly used is sodium hydroxide. We all know the formula for that alkali is NaOH. So what we have here is our animal fat or oil. Now we already know from the esters topic that if we see a C double bond OO, then that we have an ester link in our fat and oil. In fact, we have three. We have 1, 2, 3, where the alcohol part joins the fatty acid part. Now, when we are hydrolyzing a fat or an oil, it is between these oxygens that the bonds are going to break. And just like before, we're going to have a hydrogen go back onto the alcohol to produce glycerol, which you can see here. And also, onto the double bond O, we are going to have the O and the Na. So this means that we end up with a carboxylate ion, which has a C double bond O with a negative charge at the end, and it is attached to a positively charged sodium ion. Now, because there are three ester links that are broken here, there are 3 sodium hydroxides, that produces 3 moles of sodium stearate. Now, that is a soap. So when we react fats or oils with sodium hydroxide, we get the sodium salts of the fat or oil, and we also get glycerol produced. Remember, glycerol structure is propane 1,2,3 triol, has 3 hydroxyl groups. So that is where the 3 H's from the sodium hydroxide go. These 3 H's go here, here, and here to produce this glycerol molecule. I have drawn out an example to show you exactly where these atoms are going, but also in class we are going to do a couple of examples of these on the board so that you fully understand where all of the pieces are going to fit. So this process results in the hydrolysis of the 3 ester links. So we talked about that. So you remember your COO or Q is your ester link, and that is the bit that gets broken when you hydrolyze a fat or an oil. It produces glycerol and the sodium salt of that fatty acid. Now in our example we are using it's stearic acid, which produces sodium stearate, which is the soap. But it doesn't have to be stearic acid. It can be any fatty acid with any size carbon chain. And the 3 fatty acid chains can be different. They don't have to be the same chains. So whenever you're copying molecules like this, make sure you copy them directly from the example. So since soaps are soluble, they have to be extracted from the mixture by adding excess sodium chloride. So you add excess sodium chloride and then you filter it and you will be left with your nice soap. Now you are going to carry out this experiment in class using castor oil and very strong sodium hydroxide. So hopefully, fingers crossed, that'll work and you can produce some of your own soap in the class. So here is the example that I have drawn out. So we've got our fat or our oil, and I've drawn it out kind of more fully so that you can see. Here is the ester link 1, here is the second ester link, and the third ester link. So remember, our hydrogen from the NaOH is going to go on this side, here, here, and here, to produce the alcohol glycerol. Okay, the triol, because it's got 3 hydroxyl groups. That leaves us with an O and an Na, 3 of them, which go on this side, but they go here, here, and here, which if we draw this, I've drawn it the other way around, we get this, which is the sodium salt. In this case, it's sodium stearate. Again, we will go through more examples of this in class so that you have a couple of different ones for your jotters. So soap structure then, sodium stearate, that's the one that we just saw, C17H35 with your COO Na at the end, is a white solid and it's the most common type of soap. Each molecule consists of a long, non-polar covalent hydrocarbon tail. That's this part here. Now, usually just in a general drawing of a soap molecule, this will be identified by a jagged line. Now, remember our skeletal formula. Every time there is a corner, that means there is a carbon. So this long chain here is your non-polar tail, if you will. And we also have a polar ionic head where the charge is. So this part of the molecule, the head of it, is going to be where our C double bond O, O negative, and Na plus are found, whereas the non-polar tail is going to be the fatty acid part, which has the 17 carbons in this case, and 35 hydrogens. But if you're just asked for a general diagram of a soap molecule, this is the kind of thing you would draw. Let's look at this in a wee bit more detail then. We have 2 new words as well. So this part, the jagged part, is the long hydrocarbon tail. So if it's a hydrocarbon, it's non-polar. Now, non-polar things, remember, do not like water. They do not want to dissolve in water. So we give them this name, which is hydrophobic. Now, if you are phobic of something, if you have a phobia, you don't like it. So hydrophobic means this group does not like water. So that's how you can remember that the tail is non-polar. It is water-hating. In other words, hydrophobic. The opposite of that is hydrophilic, which means water-loving. Now, as we can see, this charged part, this is the head of the soap, is ionic. Now, remember, all ionic substances will dissolve in water. They love water, so hydrophilic, water-loving, is this part of the soap, which is the ionic head. So water-hating is soluble in non-polar substances, and the water-loving part is soluble in polar substances like water. That's going to come in handy when we look at how soaps actually work. So the covalent tail is a hydrocarbon chain. Of course, we know already that that means it's non-polar and can bond easily to a greasy material on fabric or skin, or a frying pan. This part of the soap is said to be hydrophobic, like we just discussed. That means water-hating. The ionic head is attracted to the polar covalent water molecules. This part of the soap molecule is said to be water-loving. So you have the tail dissolving in the grease, the head dissolving in the water, and what soap does is it does this so-called roll-up mechanism, something that you definitely need to be able to draw, whereby it forms little balls of grease, which are then suspended in the water and can be rinsed away. Here is what that mechanism looks like. It looks complicated the first time you see it, but once you've practiced drawing it a couple of times, it does get quite straightforward. If there happened to be an open-ended question about soaps and emulsions, then this would be the type of diagram, along with the soap molecule, that I would be expecting to see from everybody. So here we have our surface and our grease. I like to think of it as like a frying pan that you've just fried an egg in. The surface is nice and flat and you have just a pool of oil or grease that you want to get off. So what these little kind of white things are the soap molecules, and the blue is water. So let's have a look at how this mechanism works. Well, first of all, like we just said, the tails of the soap molecules, so the non-polar ones, the hydrophobic ones, will dissolve in the grease. So as you can see, the full tail is in the grease, and the ionic head, I don't know if you can see it here, but on the slide it has like a wee negative charge in the middle of it, I think. Might not. The ionic part, the ionic head, is dissolved in the water. Now when you're drawing this, make sure that the whole tail of the soap molecule is in the grease. If you draw it half and half, you won't get the marks. So be careful with that. Once the soap is in there, like I said, it's a kind of roll-up mechanism. What the soap molecules do is they try and surround all of the grease, like shown in the diagram here, and it ends up breaking into little balls. Now, these little balls are called globules. So they're little fat globules which are being separated by the soap molecules. Now, at the end, it's going to look like this, where the charged part of the soap molecules are going to repel each other. Okay, so they're not going to get too close to each other, and because they are repelling each other, they are going to be suspended throughout the water, but separate from each other. So the balls cannot form the big pool of grease again. They are droplets or globules of grease which are separated throughout or suspended throughout the water. And that leaves your surface nice and clean. Now, something that I need to mention about this. If you, with all the will in the world, put a frying pan with lots of grease on it and some fairy liquid in it, and just left it sitting on the counter, is it going to clean itself? Well, the answer is no. As much as we would love these little soap molecules to just go and do that by themselves, what we need to do is we need some agitation for this to actually work. So that's why when you get a sponge or a little scrubbing brush and you start scrubbing your frying pan to get all the grease off, it starts to kind of mix the soap up with the water, and this is what's going on a molecular level. So you must have agitation for this to work. That's why we require sponges and things to wash dishes. So, soapless detergents. When soap is used in hard water, a white solid precipitate we call soap scum forms. I'm sure you've all seen this before. It looks like this. We happen to have very nice soft water in Scotland, but the further down south you go, the harder the water becomes. Now, it's because there are charged calcium and magnesium ions present in the hard water, and they react with the soap to form insoluble salts or substances. Detergents are the cleaning agents which work in a very similar way to soap, but they don't form these insoluble salts. So that means that instead of getting that soap scum that looks horrible and you need lots of vinegar to dissolve and get off, they can form a nice lather like we can do with soaps in Scotland with our soft water. Alkyl benzene sulfonates are these detergents. So like soap, they have a long chain of carbon and hydrogen atoms, so that's your covalent hydrophobic tail, and an ionic head. So because they look exactly the same, they work in exactly the same way. The only difference is instead of having a carboxylate group, they have a sulfonate group, which is an SO3- group. So the calcium salt of a sulfonate is soluble in water, but if you have a calcium salt of a carboxylate, then that's insoluble and is going to produce that horrible looking kind of soap scum that you see in the diagram there. So, emulsifiers. An emulsifier is made by reaction of edible oils with glycerol. You have to know that. I've seen that come up in exam questions before. So emulsifiers, you need to react glycerol with an edible oil. Emulsifier can be used to prevent polar and non-polar liquids separating into layers. So for example, and a couple of minutes ago when we were talking about the grease particles mixed in soapy water in a dirty frying pan, that would be an example of an emulsion. Once all of the soap molecules have formed globules with the fat or oil, and these are dispersed throughout the water, that is an example of an emulsion. What the soap is doing is it is stopping the oil and the water from separating into layers. It's keeping them mixed together. So what the soap is doing in that situation is acting as an emulsifier, which helps to just bring the two, the water and oil together. That means if the oil's dispersed throughout the water and you rinse it under the tap, you're going to get rid of all those grease particles. But this is also useful in preserving food as well. Some common things that separate. Number one, milk. If you leave milk out on the counter and don't cool it down or just kind of leave it sitting for a long time, it will usually separate into the polar and non-polar constituents. So milk has a lot of fats in it, but it also has water in it as well. So if you leave milk for a long time, it will end up separating into layers. But what keeps it from doing that? Emulsifiers. So there's emulsifiers in milk which stop it separating into layers while it's in date. Mayonnaise as well is an example of an emulsion, so it will contain emulsifiers, things that keep, again, the oil and water type substances together. So ice cream is another example. These are all emulsions. So emulsifiers are really just substances that are added to foods and lots of different substances like makeup and kind of beauty creams and stuff to stop them separating into their polar and non-polar parts. It keeps them dispersed through one another. So in this example here, we see that there is oil dispersed through the water, but it can happen the opposite way as well. This time there is water dispersed through the oil. It just means that the two layers are separated, and because the ionic parts of the emulsifiers repel each other, it means that the little globules can never separate into layers again. They stay dispersed through the other substance. So some questions for you then. Number one is name the type of reaction that's used to produce soaps from fats or oils. 2, name a use for sodium salts. And 3, draw a soap molecule labelling the hydrophobic and hydrophilic parts. Pause the video, have a go at these. It's only 3 marks, shouldn't take you long at all. And we'll go over the answers. So number 1 was, name the type of reaction used to produce soaps from fats and oils. Hydrolysis will get you the mark, but it is alkaline hydrolysis. That is the full answer. 2, name a use for sodium salts. They are soaps for cleaning. And 3, draw a soap molecule labelling the hydrophobic and hydrophilic parts. So you just need to draw a little circle with a kind of pointed hydrocarbon tail. The tail part labelled as the hydrophobic part, and the head labelled as the hydrophilic part. So we wanted to be able to identify and label soap structures and describe how a soap cleans, state what's meant by an emulsion, and give an example. Hopefully, after watching this, you're able to do all of those things. Remember, you will make soap in class and also go through some more examples of different fats and oils being hydrolyzed to form soaps. Thank you for watching, and I'll see you soon.